everyone. So I'm going to keep this video short. And until last time, we've been talking about energy balance for closed systems, specifically the first law of thermodynamics in terms of the relationship between energy and heat and work. And now we're going to move on to analyzing energy for different types of cycles. But before we do that, we need to remember what a thermodynamic cycle was defined as. So the definition was that any system that goes through processes and finally returns to an initial state, that system has executed a thermodynamic cycle. Okay, so a thermodynamic cycle only happens if the system is returned to its initial state. And there are many important applications that involve thermodynamic cycles, and it's important, that's why, to understand what they are and how they work, especially when we're talking about power generation or applications like refrigeration and air conditioning. So it's important to understand and build up your understanding of what thermodynamic cycles are. But in this section, in this video, we're only going to be concerned with understanding what cycles are from the perspective of the first law of thermodynamics, which is the conservation of energy principle. We're not going to be looking at the second law, only the first law of thermodynamics. So moving on to what the energy balance equation is going to look like for a thermodynamic cycle. We already saw this expression, energy in terms of heat and work, where energy transfers are taking place due to heat and due to work. This equation we already saw. This is the basic equation for the first law. And we can apply this equation onto a thermodynamic cycle as well. And here, these represent Q cycle and W cycle represent the amount of heat, amounts of energy transfers taking place because of work and heat. But because the system has to return to its initial state, that means that there is no net change in the energy of the system. So that's why this term goes out, it cancels out. And what we are left with is just these two terms. And this equation itself is now an expression of the conservation of energy principle, and it must be satisfied by every thermodynamic cycle. It doesn't matter what the sequence of processes was, doesn't matter what the nature of the substances are in the system, this equation has to be satisfied by every thermodynamic cycle. Okay, so moving on, we have usually two different classes of cycles, two different classes of thermodynamic cycles. First, we have the power cycles, and then we loop in refrigeration and heat pump cycles together. So first of all, we're going to be looking at power cycles. And let's say that we have a system here that is undergoing a cycle while it is communicating thermally with the hot body and the cold body. And during each cycle, there is also a net amount of energy that is being exchanged with the surroundings by doing work. So we have a particular amount of heat coming into the system. That heat is being utilized to do some work, and some of that heat is being exhausted out now to the cold body. And the directions are basically indicating, the direction of arrows is indicating how the transfer is taking place, instead of looking at it in terms of work done on the system or work done by the system. We're just going to utilize these arrow directions instead. So, but we need to define what a power cycle is. So any cycles that deliver a net work transfer of energy to their surroundings during each cycle are known as power cycles. So we already had this equation, and because the net work output is equal to the net heat transfer to the cycle, so that means that the work done across the cycle is going to be heat being transferred into the system minus heat being transferred out of the system. And now we need to, one of the most important parameters to analyze these cycles is their performance. And the performance of a system that is undergoing a power cycle, it can be described in terms of the heat that is being added in, and then how much of this heat is being converted into work. Okay, and the more work we generate, the maximum performance we will have, and this performance is usually known as thermal efficiency. So we are transferring in heat, and now it depends on the system how much of this heat it can extract and convert into work. Okay, so the more that it does that, the higher the performance of that system is going to be, the higher the thermal efficiency of the system is going to be. So just remember that performance is desired output by required input. So the input during the power cycles was the heat that was being given in to the system, and the desired output is the work that we are taking out of that system. So this is how we can represent the performance of these power cycles, the work that we are taking out of the system, and the heat that we are supplying into the system. And this is called thermal efficiency of a power cycle. And now we already know that we've written the expression for the work done across the cycle as this. So all we have to do is we just have to plug that in, and we can also write the thermal efficiency of a power cycle as this, right? And now remember that because energy is being conserved, it means that the thermal efficiency can never be greater than 100%. What that means is that the work done across the cycle can only be a maximum of the heat that is being supplied in. The work done cannot be greater than the heat that is being supplied in because energy is conserved. If we had, say, a higher amount of work done than the heat that we are supplying in, then it would break the first law. Then that means that energy is not being conserved. Energy is being created somewhere. That cannot happen. So that cannot happen. But what we experience with actual power cycles is that the value of thermal efficiency is way lower than just 100% here. Okay, that means that all the energy that is being added to the system by heat transfer is not being converted into work. A portion of it is being discharged out to the cold body by heat transfer. Okay, so what does that mean? That the thermal efficiency of every power cycle must be less than 1. Okay. So moving on now, looking at refrigeration and heat pump cycles, they have the same objectives, and the objective for a refrigeration cycle is to basically cool a refrigerated space wherever it is in the building below that of the surroundings. Okay. So if we have, say, we are supplying work into the system here to make sure that we are collecting heat Q in out of this cold body, so this cold body gets even colder, and then we're supplying heat out to the surroundings, to the hot body now. This is the objective of a refrigeration cycle. And what is the difference of a refrigeration cycle from a heat pump cycle? For a heat pump cycle, we are trying to maintain the temperature within that building above that of the surroundings. Okay. Now, the only thing that has changed between refrigeration cycle and a heat pump cycle is the temperatures at which this cycle is working at. On one hand, we had the refrigeration cycle where the cold body's temperature was way colder than the surroundings, and over here the temperature of this body is above that of the surroundings. Okay, so this is the body that we are looking at for a heat pump cycle. Let me explain this again. For the refrigeration cycle, this body is what we were interested in. Let's say this is the room, or let's say this is the refrigerator that we are trying to cool. So it's already cold, but we are trying to make it colder. So we have to transfer energy out of this cold body. For the heat pump cycle, we are interested in this body. This is, let's say, our room, and these are our surroundings, and we want to increase the temperature within this hot body. So we have to supply heat into this system, into this body. Okay? And because both of these cycles have different objectives, their performance parameters, instead of calling them efficiencies, we call them coefficients of performance. And they're defined differently as well because obviously we're interested in different bodies. And again, the direction of work done is the opposite for refrigeration and heat pump cycles. Uh, and basically, the coefficient of performance for a refrigeration cycle, we are interested because we are interested in this body. So Qn is what we are interested in. Okay, we're again in terms of performance, it's required input by desired output by required input. So the required input was the work done across the cycle, and the desired output was Qn. Okay. For again, you can also write it in terms of this. So you can simplify it. And for the heat pump cycle, the coefficient of performance is going to be equal to, again, let's look at it. It's desired output by required input. The desired output here is Q out. And the required input is the work done across the cycle. So this is what the difference between a refrigeration and a heat pump cycle is. They're both operating using the same situations. You can look at them, but what we are interested in for a refrigeration cycle is completely different from a heat pump cycle. And yeah, this is it for this lecture. I'll leave some examples as home assignment for you guys. So until next lecture.